Okay, good. So then code it. So HDX. So let me just remind you quickly what we discussed last time, and then our goal for today is to prove Oppenheim theorem, which, to remind you, is a way of showing that if the top links of an expander are, of a complex are expanding, and all the bottom links are just merely connected, that's enough to prove that everything is expanding, which is a really useful theorem. So let me just first start by reminding you of, just briefly the definitions we saw last time. Just make sure we're on the same page here. So we'll be working with a weighted complex. And just it's going to be d-dimensional. So let me remind you what it is. So a complex, so by complex, we will always mean a simplicial complex. So I want to keep saying simplicial right in it, simplicial complex. That we write X, which is X0 union XD. So XD is some subsets, sets of size D. So it's a set of the top level faces. And XK is all these sets S such that the side of S is K, and there exists some T in XD, or S is a subset of T. So we just take the downward closure of the top faces. So the top faces completely determine the rest of the complex. And what was the weight? So the weights are basically distributions over the different levels. So we denote it by pi, which was small pi 0 up to small pi d, where again, pi d is some distribution over xd. So it's some arbitrary distribution over the top level faces, and then everything else is derived from it. So let me remind you, so for k less than d, if we want to sample a face, let's say sigma, from pi k, we do the following process. First, we're going to sample some face tau from the top dimensional face, and then we're going to choose, then we're going to sample sigma inside tau, size k uniformly. So again, we have the top level distribution, and we sample from that, and then if you want to go to level k, we just choose a random k subset output uniformly. So again, the top level faces of the complex determine everything below it, and the top level distribution determines everything below it. Okay. So far, this is just a quick reminder of what we've seen last time. Any questions on that? I mean, something that was not clear last time, maybe? Oh, okay. And then the last thing we needed to is talking about links, because links is a way that allows us to look on, zoom in on parts of the complex. So given some face, let's say tau in xk, we define the complex x tau to be x tau 0 union x tau d minus k. So it's looking on just everything that contains this specific face, and x tau, let's say L, is all these sets sigma, whose size is L. There are disjoint from tau, and the union is inside x k plus L, right? So we're looking on a face tau of size k, and we'll then take all the faces that contain it and remove it from it, right? So again, another way of saying the same thing is x tau is just to take all the faces, let's do it this way, sigma minus tau, where sigma is in x, and tau is inside sigma. Again, this is like the generalization of taking the neighborhood of a node. So here we're taking the neighborhood of a face. So all the larger faces contain it. Okay, so this was the last definition we needed, and we also talked about weighted. So there's also this, you can look at the weights, right? So if you look on pi tau, this is just pi conditioned on x tau. So let me not write down the formal definition, we did last time. So if we have, like, for example, a distribution of top level faces, and we're looking on a link, then we condition on these faces coming from this link, and then we just take the conditional distribution. Because this is just a very quick recap of all these concepts we covered last time. So again, let's see if anybody had any questions on any of them. Right. And then maybe the last definition we had was that of what do we even mean that this complex is an expander and expanding? So the way we define was the following, that was our main definition. So X is a gamma expander if for every level K most d minus 2, and for every phase tau in X. Okay, for every K phase, if you look on the graph, just a graph induced by this link. So just look on nodes and edges, but not higher level phases, they form an expander. Then the graph on X tau, and by that I mean the vertices are the ones level 1 up, and the edges are the ones that are level 2 up, is a gamma expander in the usual sense that graphs are expanders. And again, there are two notions to define here. You can talk about one-sided versus two-sided. So if you recall, for expanders, we have these two different notions of expansion: the stronger notion of a two-sided expander, and then the weaker notion of a one-sided expander. And very similarly for high-dimensional complexes and expanders, we have exactly the same notions. Okay. And also there was a small technical issue here, which is this graph that we get will typically be weighted graphs, so be not regular and weighted. But we've seen, or at least we stated as fact, that everything that we've done for expanders works equally well for weighted graphs when you sort of define the adjacency metrics in the right way. So again, this is what our notion. And really what our goal is to prove today is that in order to be an expander, in order for all the faces to be an expander, because this, you should imagine this high dimensional expander as this very highly connected object. We have, nodes, and they have edges, and the edges are inside triangles and so on. So there's a lot of interconnection. And actually, because of all this interconnection, what we're going to prove, this Oppenheim theorem, is that if the top level faces, the one that actually graphs, are actually expanders, and all the rest are connected, that's enough for the whole complex to be an expander. And this also sort of resolves one of the things we discussed last time, which was we had this other definition of just top faces or all the faces. They're basically the same up to constants, or from constants depending on the depth of or dimension of the complex. So let me state now Oppenheim theorem, this is going to be one of our main goals for today to prove. Okay, so this will be a theorem called the Trickling down theorem. By Oppenheim. It says the following thing. Let X pi be a weighted d-dimensional complex and assume two things. So assume, so one would be that only the top level faces are going to expand. Remember, is this a d-dimensional complex? We need to look on faces of level d-2. So they have nodes and edges. So it's actually the graph there. So for every face tau in X d-2, X tau is a gamma expander. As a graph, Now, remember, this is as a graph, right? Because when we're at level d minus 2, then we have, d minus 1 and d, which just give us the nodes and the edges. And actually, we're going to see that actually verifying that is sometimes much easier than lower level complexes, because they have these things we've seen applications later on have simpler combinatorial structure. So this is one condition. And, okay, sorry, Max, you're up. I have an alarm here.
Okay. Give me a sec to connect stuff.
Wild.
Let me remind myself of where. Right. Okay. Can people see my screen?
Yes.
Okay. Let me just do a writing check. Okay. Let's make sure that this works. People can see scribbles.
Yeah.
Yes. Okay. Awesome. Okay, so Shachar was midway through stating Oppenheim's theorem. Let me just rewrite where we were. So this is Oppenheim's trickle-down theorem, or trickling down theorem. And as Shachar was saying, it's basically stating the equivalence between these two kind of definitions of local spectral expanders. One in which kind of only the level d minus 2 links are their underlying graphs are spectral expanders, versus kind of the underlying graphs of every link in the complex, including of the empty set. So some kind of global information is a spectral, either a two-sided or a one-sided spectral expander. Okay, so Oppenheim's trickling down theorem says kind of let x pi be a. So I guess I should say we're always considering pure simplicial complexes, as Shachar defined last time. I guess a pure, or and he went back over it this time. The pure simplicial complexes are when you define everything by the top level faces and then you downward close. So we'll never have like a mid-level face that's not contained in a top one. We always assume our complexes are pure. So whenever I write a simplicial complex, I'll always be assuming it's pure. So let x pi be a d-dimensional, weighted simplicial complex. That satisfies the following properties. One, the kind of weak local spectral definition, which is that every link of dimension d minus 2 is a, so there are two versions of this theorem. There's a version for two-sided local spectral expansion and a version for one-sided local spectral expansion. We're going to prove the one-sided version in class, and the two-sided version is on your homework. So one-sided gamma spectral expander. So this only bounds lambda 2. So I guess by every link, I mean the graph underlying, sorry, the d minus 2 links are graphs. So actually it doesn't matter. And the second is that everything is connected. So we're going to have to assume everything is connected. We'll see in a second why that's the case. This is in fact a necessary assumption. So the second is that every link of dimension kind of at most d minus 2 is connected. And then the implication is that this implies that x pi is a, again, one-sided for our case, although it's true for two-sided as well, as long as you assume the links are two-sided spectral expanders, is a one-sided. So you lose some, like Shahar was mentioning, you lose some constant factor in the dimension, but 1 minus gamma over 1 minus d, I think 1 minus d minus 2, maybe technically gamma local spectral expander. Okay. Any questions on the theorem statement? So really, this is just saying that if your d minus 2 links, if like the top, basically if you're kind of, so why d minus 2, right? If you try to take a link of a d minus 1 face, what happens? You just get a set of vertices. It's not even a graph, right? It's just some set of disconnected vertices. So it doesn't make sense to say anything about these. So the first kind of non-trivial level to look at is d minus 2. And these are like a set of local graphs at the top level of the complex. And the claim here is that somehow kind of the spectral expansion of these top level graphs trickles down the complex. And you get spectral expansion kind of all the way down. That's the main idea here. And as Shahar was saying, this is a very useful theorem because we'll see kind of links of generic level are often complicated, whereas links of level d minus 2 sometimes have kind of nice combinatorial structure that you can exploit to prove that something is a high dimensional expander. Okay, if there are no questions, let's start. Oh yeah.
So the second point of the statement is when you say every link is connected, you mean like the graph underlying that?
I do mean that.
Okay.
That is a good question. Underlying graph of every link is connected.
We had a siren, so we had to go away. We returned just now. Shahar is talking to his wife. He's just coming.
All right, thank you.
Sorry for the...
Robin, stay safe.
Shahar doesn't like that I talk to you. I'm his mother.
Fine, everything is good. Perfect.
Until next time.
Until next time, yeah. You might have a few more missiles coming.
All right, I didn't really manage to make much progress. We stated the full theorem and said things about it.
Perfect, good.
You can go into the proof now.
Okay, nice, perfect, okay. Okay, so let me go back to share my screen. Okay. With the next row, let me just quickly finish it here so that we have trees in here. So for every tau in X. So for every K, most D minus 2, for every tau in XK, X tau is connected. So just a very, very weak condition. And I'll discuss this condition later. It's actually a necessary condition. Then X is a gamma high dimensional expander. Okay, so it's a theorem. So the one thing that's nice here in the proof is actually, although it is stated like general D, it's actually the most interesting case is D equal to 3. Just a 3-dimensional complex. So a 3-dimensional complex is basically, so the fact that what we're going to do here with the proof, we're going to see 2 parts. The easy part is going to be that it's enough to prove. Enough to prove for D, which is 3. And then the hard part is going to be proving it for D equal to 3. Okay, that's going to be what we're going to pick. But maybe before doing that, let me just, because I know sometimes it's hard to get intuition. So let me just draw a picture here. So what is D equal to 3? So basically, I mean, I think a good example to have is that, think of even a graph, right? Let's say I have my graph here. Maybe there's something like that. So I have a bunch of triangles in my graph. And then I have a bunch of edges and I have a bunch of nodes. And think of them as a 3-dimensional complex. So maybe, if you should think about V as the vertices, E as the edges, and T on the triangles. So this is a three-dimensional complex. And so what this theorem tells us is that if you want to prove this complex is expanding, it's enough to take nodes and look at the neighborhood of a node. And the neighborhood of a node is going to be what? It's going to be all the edges that touch it and all the triangles that touch it. So it's going to define a graph. And if this graph is expanded for every node, and if the overall graph of the whole complex is just connected, then also the graph underlying the empty sets. The graph under the actual graph here is an expander. And and then also you can do it. So I made this one mistake here. This is not gamma. This is slightly worse. Actually, we're going to pay something here. I actually should have caught that. This is going to be slightly worse than gamma. It's going to be.
Yeah, I should have. I wrote it correctly when I did it a few seconds ago.
Yeah, sort of not in an ideal scenario here. I might be a bit distracted.
I think I was more upset with your use of HDX instead of local spectral expander, and so I missed it.
Oh, I'm sorry. Yeah, fair enough. You're right. That's the local spectral expander. That is a very good comment because, like I told you, there is no one definition of what is an HDX. There are like many definitions, and none of them are equivalent to each other. Some imply each other in other ones, but it's good to be precise. And what notion of expander do we mean? So this is a local spectral expander. So in the sense, all the links are the local graphs are expanders, and we'll see. Maybe on Thursday or maybe next week, that this notion implies other notions of expansion that are important in applications, like for example, that random walks mix fast. Okay, good. So we lose something, but maybe if you think of gamma as really small, and maybe D is not too big, so it's maybe not that bad that we lose something here. Also, a nice cool fact here is if gamma is 0 or less than 0, let's say 0, then you lose nothing. This actually turns out to be really important in some applications. Some applications actually can prove that the top dimensional faces are at 0, like one-sided 0 expander. So all the eigenvalues are, except for one, are 0 or negative. And then you can take it all the way down and you lose nothing, right? If you plug in gamma equal to 0, then you get 0. If gamma is negative, you get even a larger in absolute value, negative value. It's the only gain. And that's another cool fact. Okay, so let's so any questions on what we're trying to prove before we start diving into the proof? All right. So let me first show you why it's enough to prove for d equal to 3. So just a reduction to d equal to 3. So basically, we're going to do it by induction. So let's x, and I won't write x pi unless I have to mention pi x specifically. Let x be a d-dimensional complex that satisfies the assumptions. So I want to argue that in particular, for every tau in x1, every node here, the link of this node also satisfies the assumption. So this is going to be a d-1 dimensional complex that also satisfies the assumptions. Right, so by induction, it's going to be an expander. So x tau, so by induction, x tau is a local spectral expander. And what value do we get here? Well, we're going to plug into the formula instead of d-1. So it's going to be gamma over 1 minus d minus 3 gamma, local spectral expander. Right? So now what do we know? So now I'm claiming, well, what is the one thing that we don't know? So we know something about all of the links, right? So we know something about the graphs of all the links. So there's just one graph that we don't know is an expander. Which graph is it? Anybody? Think about it. Let me just do it. So you can think, okay, let me give you another picture because it's going to be good. It's also good to think about complexes as sort of, this layered graph where we have nodes here, and here we have the edges. And here we have the triangles. And we just connect a node to an edge. If it appears in the edge, and we connect an edge to a triangle. If it appears in the triangle, and so on. Right? So you can view this as a layered graph. And here we have, basically x0. And we know that from every node here that we start, and we look here in its neighborhood, all the graph that you see. So from here, what you're going to see nodes in x2 and edges in x3, and they're going to define an expander. And you're going to see nodes in x2 and also going up because we proved by induction. So we covered all the graphs we could get with all the links we could get, except for just one. The only one we haven't proven is the one for actually the base graph for this complex. But think about it. If you just want to prove for the base graph of this complex, and this complex might go on many levels, we don't need to explore everything. We can just truncate it here. We can look at what's called a truncated complex just for the first 3 levels, x0, x1, x2, x3. So it says like, nodes, edges, and triangles, and we just ignore everything else. What is this? This is a complex that satisfies the assumptions. So this I want to argue here that what's called 3 skeleton of X, which is x0 union x1 union x2 union x3. It also satisfies the assumptions because all the links, the top level links, which are here just x1, they're expanders. So this satisfies the assumption, but not with gamma, but with this worst value of gamma. With, let's call this maybe gamma prime, which is gamma over 1 minus d minus 3 gamma. So again, because we assume it's 2 for d equal to 3, we can again apply it here. So by as theorem holds for d equal to 3, we get that the graph of x is a gamma prime over 1 minus gamma prime expand. Again, just plug in here d equal to 3 into the theorem we had here. Here the theorem. So plug in d equal to 3 here, I get 1. And then it's just simple math to see that this gamma prime over 1 minus gamma prime exactly equals to what we were trying to get, gamma over 1 minus d minus 2 gamma. So this is a proof. So basically what this proof teaches us is that all of the complexity of this problem is already present when we look at 3-dimensional expanders. But just one level beyond graphs. We have nodes, we have edges, and we have triangles. And already this 3-dimensional structure captures all of the complexity of higher dimensional complexes because of this recursive structure.
Shahar, could you clarify why we need triangles if we're just interested in for the underlying graph for x0?
Yeah, very good question. So what do we want? What about x0? We want to argue that we can apply the theorem for x0. So I want to say the links of it, like if I take any node, its neighborhood should be an expander. What is the neighborhood of a node? We need to have nodes and edges in the neighborhood of a node. They correspond to edges and triangles in the graph.
Okay.
I mean, inherently, this is a statement about something that is beyond the graph.
Mm-hmm.
We need at least 3-dimensional structure here, and it's actually enough.
Okay, got it. Thank you.
Perfect. Next, I'm wondering if we can try to time the missiles to the annoying parts of the proof. Just to put them in, we'll see. Or maybe they're done, I don't know. Okay.
Yeah, just time Garland's method at the right.
Exactly, yeah.
Right.
Yeah. Okay. So what's going to be the idea of the proof? Well, the idea is, like Max said, is going to be Garland's method. So what is this Garland method? So this is it's a buzzword. So let me tell you what this buzzword is. Well, Garland's method is just this general, I would say, phenomena that exists in complexes that said local behavior in links translates to global behavior. And also you can express global averages by local averages on links. So this sounds sort of very sort of, abstract and unclear. So I want to give you a very concrete notion of what we mean here. And that's going to be sort of the main technical part underlying this proof. And now the proof will not be technical, but it will be conceptually, I think, very interesting. So, but first let me make some definitions. So again, we have this complex. We will need to study functions on this complex. So given K between 0 and D, let Ck be the space of all functions from the kth level to the real. So you should think of that as assigning some real values to anything in the kth level. Like, for example, our distribution on the kth level is such a mapping, right? And also I'll define the expectation of F. So given F for F in Ck, the expectation of F is going to be what? Well, remember that we're working with a weighted complex, and we have an underlying distribution for the kth level. So we're going to use this underlying distribution to look on the expectation. So it's going to be the sum of all faces in the kth level, the distribution, the probability that we see this face, times F sigma. And actually, and the last thing I want to define is that if I have two functions here, F and G in Ck, the inner product is just going to be the expectation of Fg. Okay. So we now can define expectations and inner products over functions. And one thing that will be really useful here is, remember our distributions pi k here they're all interconnected, right? They all come from this top level distribution that we push all the way down. And we'll say this interconnect is going to be really crucial for us. It would allow us to express notions of pi k instead of pi k minus 1, pi k plus 1, go back and forth. That will be extremely useful for us. Okay, now I want to talk about links. And so I need, again, one more definition. So now let V be something in X1, like a node in my complex of nodes, edges, triangles. So we need to define the notion of a localization. And that's also a function F to be in Ck. So let me define it more generally let me define the notion of localization in a more general way. We need to apply it for X1 here, but let me define it more generally. Another definition. So let F be a function in Ck and tau be some face in XL. Could be the same, could be different. So the localization of F at tau is going to be a function that we're going to denote F tau is going to be living in Ck of the complex X tau. So before, when I wrote Ck, if I want to specifically what the complex is, I write Ck of X. So it's going to be, I'm going to go to the kth level of the links of tau. So they correspond to faces of level K plus L in the original complex. And it's going to be defined the following way. F tau of sigma is F sigma, whenever it's defined. So okay, this might seem mysterious. What do I mean by that? So again, let's think about this three-dimensional object. So we have these nodes, and we have our edges. And maybe here we have a triangle. So let's say I have a function here, and my function gives values to nodes. Let's say I have a function f, this is an example. Let's say I have a function in C1 of x. But some function that gives weights to nodes. Maybe I'm going to give them the weights 1, 2, 3, 4. Well, what is a function f localized of 1? When we want to look at the node 1, and we're looking at its neighborhood. So its neighborhood is going to have two edges, right? It's going to be this edge and this edge. And it corresponds to two nodes, 2 and 4. So F1 is going to be basically saying, just going to look at these two nodes, and we're going to give them the weights. We're going to have this sort of, this triangle is going to become an edge here, and we're going to give it the weights 2 and 4. So basically what we're doing here is we're just looking at all the faces that are adjacent to the node that we cared about. We remove all the rest and we keep the value the same. Okay, so F1 of the top node here, again, let's give these nodes names. Let's call them A, B, C, D maybe. So this is going to be node B, it's going to get the value 2. This is going to be node D, it's going to get the value 4. We don't have the node 1 A here because we remove it in the link, and we don't have the node C here because it's not in the neighborhood of 1. Okay, so this is the notion of a localization. Okay, it's sort of like a restriction of some sense, right? And I need maybe one last definition here. Last definition. So again, given k at most d minus 2 and some tau in xk. Remember what we're looking at is that the graph that lies in this complex. So we're going to let a tau denote the adjacency matrix of the graph. Underline x tau. And I just want to remind you, so A tau is basically the graph that we're looking at. And I just want to remind you that, when we look on weighted graphs, so it's graphs with weights on the edges, the way we define the adjacency matrix is a bit different than what we did before. So just again, a reminder. So if G is the graph, and we have some weights, then we define the adjacency matrix as follows. So the VW entry is going to be the weight of the edge VW normalized by the sum of all the edges that touch V. The sum of all U, all the U, sorry. It is adjacent to V, pi E, V, U. So again, this is sort of like the random walk probability, right? So we go, should think of it the same, what's the probability of going from V to W? Well, it should be the weight of the V to W, but normalized so that the sum of the probabilities is 1. So we divide by the sum of all the weights of the edges. And also these are always going to be non-negative. That's important. So we're always going to have non-negative weights when we try to define adjacency matrices. And for us, they're going to come from pi of the distribution on the top faces. That's always going to be non-negative. And we've seen that this has an eigen. So we've seen that A has an eigen decomposition in the same way that we've seen for regular unweighted graphs, and that lambda 1 is 1 with the eigenvector 1. It just means that A1 is 1. And then the last thing I want to remind you of is that we can view A as an averaging operator when you act on the right. So if F is now a function from the nodes to R, then AF in a node V is the average of F when we choose a random neighbor of V. And again, the probability is again the same thing. It's a weighted. This probability is weighted by the weight of the edge. And so we've seen it last time, so this is just a very quick recap. And now let me sort of state, after we've seen all these definitions here, let me now state Garland's method. What we need for this. But maybe before that, let me just state what we're trying to prove here using Garland's method. Let me first just state, Oppenheim theorem for the case of d equal to 3. Just so it's clear. So we're just going to be focusing on this specific case for the rest of the lecture. So let X be a three-dimensional simplicial complex. And we assume what? Well, we assume one, that is for every node level 1, the matrix, so the underlying complex is a gamma expander. And to remind, this is the same as assuming that the second eigenvalue of AV is at most gamma. Okay, and also we're going to prove it just for the one-sided case. For the one-sided notion of expanders, we're going to have the two-sided as homework. They're very, very similar. So let me just focus on the one-sided case here. So we're assuming everywhere that whenever we talk about expansion, we're going to talk about one-sided expansion. So we're just going to bound the maximal eigenvalue, not the max and the min. It's slightly simpler. So this matrix AV that we defined here, right? A. So it is AV. AV, and just reminding you here, this is A tau. For general phase tau, this is the underlying adjacency matrix of the complex. In our three-dimensional case, we just look at nodes, and we look at the adjacent triangle that sit on them. They define some adjacency matrix. It is an expander. And secondly, well, there's only one lower dimensional phase. So A of the empty set, which is just the underlying, X here is connected. No, it's a graph. So if I take the underlying graph of X, it is a connected graph. Then what do we want to prove here? Well, we know that all the graphs are expanders except for the graph that sits on the bottom link. Then A of the empty set, so the underlying graph of the complex, which I'm just going to call A for simplicity, is a gamma over 1 minus gamma expander. And again, we're going to prove it for one-side expansion, and a very similar proof that you're doing homework works for two-side expansion. So this is what I want to prove to you. And in order to prove that, we're going to apply Garland method. But for simplicity, since we're only going to care about three-dimensional complexes, I'm just going to write it for this specific case that we need. But later on in the class, we'll see other internations of it in higher dimensional complexes as well. So what's going to be this lemma? It's going to be one version of Garland's method.
I think before, it might be worth stating kind of before you give Garland's method, kind of where we're going with this, which is that the way that we would normally prove something like this, right, is we would look at a Rayleigh quotient and we would split F into kind of parallel and perpendicular parts. And then we would try to bound the perpendicular part by your object being an expander. And the problem here is that you can't do that over the whole complex because you don't have that information, but you can do it over links. So if you can find a way to divide things up over links, then we can just apply our standard techniques. And this is what Garland's method is going to let us do.
Perfect, perfect. Thank you, Max, thank you. So let me just write this down so it's more explicit. So what's the idea? Good. Okay, so what's the idea? So we're going to, again, apply, we're going to study, we're going to bound the Rayleigh quotient. Right, so we're going to choose some function on the nodes of the complex. It's a function in C1 of X, a function on the nodes that is orthogonal to 1. And our goal will be to bound its Rayleigh quotient. To bound, well, F transpose AF over norm F squared. Right, that's going to be our goal, like everywhere. How do we prove expansion? We bound the Rayleigh quotient. And like Max said, we cannot do this directly because we do not know that this complex is an expander. But we do know that the links are expanders. So if we could somehow reformulate this quantity as something that just depends on the links, then we can apply their expansion to bound this. And that's exactly what we're going to do. So again, the main idea here will be take this quantity that we've seen so many times in this class that we use to prove expansion, but analyze it not directly, but indirectly via its action with the links. Okay, that's where we're going. Any questions on that before we head on to the more technical part? All right. So now is a good time to tell you about this Garland method, which is going to be a way for us to do it. And then again, Garland's method is a general method. So it's not just this one specific lemma. We're going to see other versions of it coming up later on in this class. But here's our version. So again, let x pi be a three-dimensional weighted complex. And I'm going to remember that I'm going to denote A to be the adjacency matrix of the bottom link, right? So just for simplicity. So now let f and g be two functions on nodes of this complex. Then I'm claiming that the following two identities hold. One, if I want to look on the inner product of f and g, which is something on the whole complex, right? What I can equivalently write is the following thing. I'm going to choose an expectation over nodes in this complex. And I'm going to look at the function f on the localized version of f on this node and the localized version of g on this node and take their inner product. But this inner product is not over the full weighted. This is over xv of 1. So I'm going to write this here just to remind ourselves that these functions fv and gv do not live on they are not functions on the node of the complex, they are functions on the nodes of the link of v. So this is just to remind us that they sort of live in a different domain. Okay, but even though these two quantities are exactly the same. So this is sort of a version of saying the global average is the average of the local averages. So if you've ever think, that expectation of an expectation is the full expectation, expectation of a conditional expectation is the full expectation. That's the same phenomena happening here, just in a more intricate way. And the other one is going to be about the adjacency matrix of the whole graph is going to be, well, AFG is going to be, again, very similar thing, expectation over V in X1 of AV, FV, GV. And again, this lives over the XV1. So again, what do we say here? Remember, what we care about is analyzing the Rayleigh quotient of A. So we want to analyze expressions like, F transpose AF or AF inner product F. And this is in general, take any two functions F and G, AF inner product G is the expectation of the same expression, but in links. And notice that we remember, what do we know? We know that AV is an expander, it's a gamma expander. So if we can somehow massage it with FV or GV or orthogonal to the constant functions, then we can now apply the expansion property. So that's going to be the goal, right? We're going to move from global averages of the complex to local averages over links. Okay, and now proving this lemma, there are several ways you could prove it. And actually what I'm going to show you, the proof for 1 and 2. I mean, they can be done in the same way, but I want to show them in slightly different ways because I think it's going to be sort of, instructive to see them in different ways. Okay. So let's start with the proof of 1. Well, before the proof of 1, I just want to sort of make one simple claim before we prove it. So here's going to be a simple claim. This is going to help us simplify various expressions here, which is the following thing. So let's say I'm going to look on something like pi k of x tau, where tau is some L dimensional phase. In general, for some general k and L. So I'm asking, so here is L is less than k. So what I'm saying here, I'm saying take a link in some L dimensions. Look at all the faces it has in the case level. Is this what I want to do? Sorry, 1 second. Sorry. Let me say this again. Okay, I'm writing this a different way. So let's say again, we have, so here's like a general, before proving it, let me just make the following claim. It's going to be useful for us. So let L be less than K and fix some tau in XL, so some L dimensional face. And let's look on X tau, which is all the faces contain tau. And let's look on pi K of that, which is, just to remind you, that is a total weight of all the K faces that contain tau. This is just going to be the sum over pi K sigma over all sigma in XK that contain tau. So it's a total K weight of this link. I'm claiming this has a very simple formula. That's always going to be K choose L, the Lth probability of seeing tau. Okay, that's a claim. And the first part is just a definition here. This is how we defined it last time. And I'm claiming if I'm going to sum all the probability in the case level of a link, is going to be exactly going to be the probability of seeing tau when I move down to the Lth level times some scaling factor. Okay, what's a proof of that? Well, let's remember, what's a probability? What's a proof? Let's remember, what is pi L tau? How do we sample it? Well, it's going to be the probability. That's going to be the probability that we do two things. First, that we sample. Okay, how do we sample? Let me remind you. How do we sample tau in from pi L? We do it in two steps. Step one is that we sample some sigma from the, in this case, is going to be the top dimension, I would say the K dimensional faces. And step two, we sample tau inside sigma uniformly, where the side of tau is L. And I'm saying, well, what's then the probability of seeing tau? Well, we should first sum over all the probabilities of all the K faces that contain it, which is going to exactly, is going to give us this expression. But then we're going to say, well, it should be that. And then, given that we chose sigma that contains tau, the probability that we actually sample tau is, it's completely uniform over all the L subsets of the sigma. So we're going to divide by K choose L. Right? So pi L of tau, the probability that we sample tau under pi L, is exactly by definition the sum of all the probabilities of a K-dimensional face divided by K choose L. Actually, the way we defined it was just if K was a top dimensional face, but you can actually prove, I won't do it here, that the same holds for any K more than L. Okay, this might be a good exercise for you to figure out. So I'm claiming this equality holds just by the recursive way that we define lower dimensional probabilities from higher dimensional probabilities. But this stuff, the way it's defined. I mean, this might, if you don't see it now, it's fine, just take it on faith and then later on verify for yourself. Once you realize it, technically there's nothing here, just definition. But it might take you a while to internalize these definitions. So that's just going to allow us to simplify various quantities we see here. So now let's go back to the proof. Now let's prove of Garland's method, of the lemma, let's call it, of lemma. And let's start with the proof of one. For one, remember what we want is we want to analyze, or when we want to prove, we want to show that the inner product of f and g, and I remind you, f and g are function of the nodes of the complex, is exactly the same as the expectation of the length in the complex of set of vertices of the inner product of FV and GV. And I won't keep writing, but this latter inner product is defined over the link, XV of 1, right, the node of XV. So why is this true? So let's try to express this quantity, the right-hand side. Let's see what it gives us. Let's just try to expand everything and see what do we get. So the right-hand side, let me just copy it again, is the expectation over V in X1, FVGV. So let's just write what this is. Well, we expect the expectation over V, so we sum over all of V in X1 times its probability, which is pi1 of V. And then we take the inner product of FV and GV over the link of V. So it's going to be the sum of all nodes W that are in XV1, all the nodes that are adjacent to V. Of what? Well, it should be the probability that we sample W. So it should be, so let me remind this definition, pi V1 of W. So the probability that we sample W in the complex that underlies V times, well, FV is just F, it's just going to be FW GW. Sorry. FW GW. So let me remind that FV is just equal to F on its domain, right? FV just takes the value of F when it's defined, and when it's not defined. So I want you all to just take a minute to study this expression and convince yourself this is what we're trying to analyze. This is just completely spelling out all the definitions. So expectation of V is just summing over all V's with its probability. And the inner product of two functions in the link of V is just the sum of all nodes W there of, FW GW times the probability we sample W in the link of V. Again, I'm just reminding you that this is, sorry. This just equals FV W, this is equals GBW, right? So we can just already move to F and G. So how can we simplify? Well, the first thing is just ask yourself, well, how did we define this probability? Well, what is this probability? This is a conditional probability of sampling W from all the neighbors of V. So we can just spell this out. We should do that. So the first part stays the same. Now, what is this probability? Well, if you remember, it's just saying, well, it should be the probability under pi2 that we sample V and W divided by the sum of all the probability that reach V over pi2 VU over all U in X1, right? What is a conditional probability of seeing W in the link of V? If we define this last lecture, so I don't know if you remember, so we just said, well, take whatever you get from pi2 of VW, but then normalize it so it sums to 1. So we just sum over all U that is in the one link of V. And again, times the same thing. FW, GW. Now let's look on the bottom expression here. What is this? So we're looking on pi2 of all the two faces that contain V. Well, what is this? This just equals to pi2 of the link of V, right? By definition, this is just the denominator. This is just the sum of all probabilities of all two faces that contain V. And by the claim we just saw, this is just going to be up to a scaling factor, which is going to be here 2, just a pi1 of V. Okay. And this pi1V in the denominator, cancel this pi1V here. And what do we get? Let's just write this out. Well, this 2 here becomes a half. Sum of all V in X1 or W. In the link one, the probability pi2 of VW, FW, GW. So we simplify the expression. And now the next trick is to say, well, we're summing basically over nodes V and over neighborhoods of its W. So basically what we're doing here is summing over edges, VW. When we sum over edges, it doesn't matter if we first go over V and then W, or if we first sum over W and then V. So what we're going to do is exchange the order of summation, which is going to be a very useful trick here. So that's going to be by half. We're going to go over all now W in X1, V in the link of 1, well, the same pi W, pi2, VW. So just exchange the summation. So we go over all edges, over all pairs VW. So we either start by V and then go on all the W's that are neighbors of V, or the other way around. They're equivalent. But now what's the idea here? Well, this F and G just depend on W, right? So we can move them outside of the inner summation. So what do we get here? It's going to be equal to half the sum of all W X1. Well, this already gets closer to what we're trying to prove. We're trying to just get inner product of F and G over the whole complex. And now we have an expression here, where it's going to be the sum over all V in the neighborhood of W, pi2 of VW. Well, what is this expression? We've already seen that. This is exactly equal, for the same reason as above, this equals to pi2 of XW. Right? This is just the total weights of the two faces that contain the node W. And again, with the same claim we've seen before, that's twice pi1 of W. And these two here exactly cancel this half here. And what do we get here? We get the sum of all W in X1. Well, we get this pi1 W, FW, GW, which is exactly what we were trying to show in a product of F and G. So this finishes a proof of part 1. So again, so what we've done here is a bunch of algebraic manipulation. So it might be sort of, even if you can verify it line for line, maybe there's no intuition, why did this work? So I think the way you want to think about it is as the following thing. So we can, basically what we showed is that this expression we're trying to analyze can be equivalently stated as something that talks about edges, right here. There's an expression that talks about edges. And turns out that the two expressions we show are equal are just two ways of thinking about these edges. Do we first sum on V and then on W, or do we first sum on W and then on V? So it's basically changing order of summations, given us the two, this global average and the local averages are both the same. And again, another way of thinking about the same phenomena, if I have some, random variable X that depends on a random variable Y, and I look at the expectation of some random variable X that depends on some random variable Y. This is expectation over X, this is over Y. This is just the same as expectation over X, right? This is expectation of expectation, or the sum, average of averages is an average. So to some extent, this is what we're doing, except the distributions we have here are not uniform. They're exactly the one that induced from the complex, but we define them. It wasn't clear at the time, but maybe it's clear now at exactly the right way so that we can do this order, this change of, order of summation. So again, I really expect this to be not intuitive to you when I just present it here, but hopefully now, if you haven't read the notes, or if you read them and something was not clear, now you can read the notes again and try to gain some intuition into why this is true now, okay? So the proof of the second part is going to be very, very similar. So, we have like 10 minutes, which I'm hoping will be, maybe if we're going to go a few minutes over time, which I think I'm allowed, given there's a missile attack, I'm allowed to have 5 extra minutes, right? I think it's like, no. This is what, still in
actually in the UC bylaws, yeah.
Yeah, I think, you know, every missile is another 1 minute, I think, yeah. So let's do the second part. So first thing I want to just, so this is going to be part 2. So we thought there's going to be this expression AFG. And I want to claim to you that there's actually a very nice way of understanding this expression. I want to claim here that this is exactly the same as the following thing. I'm going to take all nodes, all edges VW. So I'm going to sum, sorry. Yeah, I'm going to look on all, sorry. I'm going to look on an average of all edges VW in X2. So I'm going to write VW the same as, you know, the edge VW, just for succinctness. I'm going to write just VW instead of set V comma W. But I mean the same thing, just a set of size 2. And this expectation is again over pi 2. It's just the expectation of FW GW. So why should this claim intuitively be true? What is A doing? A is basically
FV GW, right?
No, here this is what sorry, yeah, thank you. It should be FV GW. Yeah, this is what I meant to write. Thanks, Max. So what is this random walk doing? It's saying, well, you start at a node coming from some stationary distribution or from distribution, you take a random walk, you get to another edge. Well, it turns out the way we define this by choosing a random node based on pi 1, and then taking a neighbor of its condition on, well, pi 1 of this link, you get a distribution over edges, which is exactly, when I prove it soon, pi 2. And the reason is basically everything we define is based on conditional expectation. So it shouldn't be surprising. This was just the way we define pi 1 and pi 1 of a link given pi 2. So this tells us, look at this AF comma G, it's just another way of saying choose a random edge. And look at the correlation of F and G when F gets one node and G gets another node in the edge. Which is really the way we want to think about expansion. It's expansion, but it tells you that choosing a random edge in a graph decorrelates to coordinates in such a way that F and G becomes uncorrelated. So this expectation should be very close to the global expectation of expectation F times expectation G. So we will use this once we assume an expander, but this should be an intuitive way maybe to think about it. So let's maybe just prove this claim. So again, we're just going to expand the expression here, AF comma G. Well, we're going to sum over all nodes V in X1, the probability of V, and we're going to get GV AF V. And if you remember, we said, what is AFV? How does A act on the right? On functions, it acts by an averaging operator. So this is the same as the expectation of F over the neighborhood F of W, where W is in XV1. So this AF, A of a function, is just this averaging operator. So AF of a node V is the expectation of F over the neighbors of V. And how do we weigh them? Well, exactly by the distribution induced, you know, on the link of this node. So we get that. So then let's spell out what this means exactly. And we have the same thing, V X1, pi 1 V, GV. So what is this distribution? What is going to be the distribution over all nodes W that are in XV1? The probability that we see it is going to be pi 2 of VW. And with all the things that's a normalizing factor here is exactly pi 2 of XV. And this is the sum of all the weights. Contain V, again, FW. So this is exactly the probability in which we choose W in the neighborhood of V. So it's a weight of the edge VW normalized by all the sum of all the edges, the touch V, which is just said as pi 2 of XV. And we've already seen that this pi 2 of XV exactly cancel this pi 1 of v. So let's see that this is just, sorry. We've already seen that pi 2 of xv is just twice pi 1 of v, so they cancel out. So this is the same as before. So we get the sum over v in x1. Well, what do we have here? So the factor of so it's something here. Yeah, there should be a half factor here. V in x1, w in its neighborhood, pi 2 of vw, and you know, fw gv. So again, what I was saying here, we're sampling an edge probability pi 2, and we sum over v and w. We multiply them by the probability of this edge times fw/gv. Well, every edge here, vw, is sampled. Actually, in the sum appears twice because we can first choose v and then w, or we can first choose w and then v. So we can equivalently write this as just the sum over all vw in x2 pi 2 vw fw/gv. Right, again, we could sum over edges. Here we're summing over unordered edges, while above we sum over ordered edges. That is half exactly cancel this. The order edge covering every edge twice. And this is just exactly how we define, you know. This is exactly what we try to prove. This is going to be exactly the expectation over VW in X2, well, I guess FWGV, or the order doesn't matter, it will be FVGW, same thing. Which is exactly what we're trying to prove. Okay, so again, there are a bunch of algebraic manipulations here, but at the end of the day, it all follows from the fact that the way we sample a node comes from separating an edge, and then shouldn't this node be one of these two endpoints random. So everything just boils down to that once you figure out why all these algebraic manipulations work. So it's a good exercise for you to figure this out, to just go through the details later and check that they all work. There's no easy way around it. You need to actually go through it yourself and verify them and internalize these notions. It takes a while. And now I want to use this to prove the second part. And we're almost done. So we're almost done. So what is our goal? Remember, our goal is to prove that AF inner product G is the same as the expectation of our nodes in X1 of AV FB GV. Okay. Now remember, what was our trick before? The trick before was we cared about functions on nodes, and we said, well, first sample an edge of size 2, and then go to a node, taking one of its endpoints randomly. Well, we didn't do it explicitly, but do it implicitly. Well, now we're going to use the same idea, but do it explicitly. Except now we care about edges between F and G, so we're going to go one level up. We're going to say, first choose a random triangle, and then choose the edge by one of the 3 edges touching this triangle uniformly. So I want to say that if I choose a triangle from pi 3, and then I choose one of its edges randomly, then this is going to be distributed like pi 2. Okay, that's because this is exactly the way we define our distributions, the way they trickle down from the top level to the bottom level. So how are we going to use that? Well, let's start with the left-hand side. So we have AFG, which is by the lemma we just proved, just the expectation of the edges PW. Or let me just stick with the letter names I have in the notes. Let's do what's called UV here. UV next to FUGV. And what we're going to say that, well, here's another way of picking this edge. Pick a random triangle, UVW, in X3, and U and V are just going to be 2 of its endpoints randomly. But I'm going to think of UVW here as an ordered triangle, an ordered triple, just for simplicity. So think of it as an ordered triple, FUGV. So again, all I'm saying here is choose a random edge is the same as choose a random triangle, and then choose, a random edge inside it. And here you should think of UVW as an ordered triple here. So now what can we say? Because it's the same as first choosing W in X1, and then choosing this pair UV in XW of 1. So this is just a conditional distribution. So again, we want to choose a triangle now. So we're going to first choose this one node W, and then choose this edge to be a random edge touching this node. And that's the same thing, FUGV. But this is exactly what we have. This is exactly, right? If we look on the link of W, this is exactly a different color here. And now we're in the link of W. So think about this internal expression here. So this one is the same as the localized version of W on U. This is a localized version of W of V. This is just going to be, by the same claim we had before, the action of the adjacency matrix in the localized version of W. That's going to be AW, FW, sorry, this should be G, GW. So overall, this again follow for the same claim, but now applying it inside the link, not globally. The link, the claim here, where we said that this claim, connect, given this, other way of thinking about A of comma G, or the action of A on two vectors, F and G. They actually measure the correlation under a random edge in the graph. So overall, we got exactly what we're trying to get here, which is going to be the expectation of W in X1 from pi 1, AW, FW, GW. Okay, and this finishes the proof of the second part. So again, I suspect that for many of you, this might just look at algebraic manipulations. But I try to give you at least some intuition, and I think now it'd be very, very instructive if before the next lecture, you all go through the notes and you go through these calculations carefully and you make sure that you understand them. Because we're going to do these tricks a lot. Sampling edges by going, well, let's first sample a triangle, then sample an edge inside it, or let's sample then, or go sample a node, sample an edge in its link. So we go all these conditional expectations again, and you need to become familiar with them because we will not write them in full detail, every time. So this is, I think, this is a really good exercise for you to just verify that you understand these definitions of how we define the probabilities of levels, how we define the probabilities over links, and so on. Okay, so now I think it's a good time to stop. So what we're gonna do next lecture, well, first I'll briefly remind you of that, and then we will see how we can use Garland's method, this global to local equivalence, to prove Oppenheim's theorem. Okay, so that's going to be our task for next time. And then I think we'll have enough time to also discuss some concepts of can we even get sparse high dimensional expanders. We've seen for graphs, we saw two proofs of how to construct sparse expanders, but we've seen there are many more. So we'll discuss this question for high dimensional expanders, which so far is much less understood compared to the graph analog. And so I'll try to explain why next time, why it's a much harder question, and what do we know about it. But to a large extent, we're still in the dark on this question. I mean, we have some knowledge, but there's more unknown than known. Yeah, that's it. Any questions? So I don't know. I think to me, it's the first time I'm teaching a class while there's a missile attack. So that was the first.
Did it stop, or is it still going?
It stopped, but I'm expecting there will be more missiles during the night, so probably have to go. So basically, I'm at my parents' apartment, so we go to there's like a staircase for the building, so we just go there, so it's safer there if a missile hits it. Although I'm assuming if a missile is going to hit the building, then the building, although these missiles are small, so it's not clear. We'll see.
Are you like safe?
Oh, no. That's part of the reality of living in Israel. You know, there's always some element of risk going on. I mean, I think it's one of the first of those missiles from Gaza into central Israel. I mean, there have been many, many missiles in the past to the southern parts of Israel, but now there seems to be a escalation, and you know, so I chose a good time to come and visit. That's what I chose. So it's never boring. Yeah. Good. Okay. So maybe let's stop for today, and then we will continue next time. Hopefully, with quieter lecture and yeah, more fun stuff. Okay. See you.
Stay safe, Professor.
Thank you.
Stay safe.
Thank you.